what are some of the challenges of teaching the unseeable, particularly in chemistry? Well, there's the obvious one, you can't see it. So can't see, you can't really draw it, you can't show a picture of it, you can't describe a physical reality that no one has ever seen. So I'm particularly talking about things like atoms here, which even with our best telescopes, we can't microscopes, we can't literally see, right? We can get topographical maps, all kinds of enhanced images, but at no point can we actually see an atom. So that's a big challenge when most of what you talk about is the atom. Also, most of chemistry is model-based, so my high school chemistry teacher, who I still have a big idol worship for, I guess, used to say that science is sort of this process of building a mental model and trying to apply it and then fixing it where it doesn't work and rebuilding your mental model over and over and over again. And so that's an idea that I think I try to infuse in all my teaching. I try to encourage my students to develop their own mental model and use it until it doesn't work right anymore, and then tweak it so that it does work again. And I think that's actually really true of the process in real world science as well, right? So our understanding of most physical phenomenon is based on some kind of mental model that has been applied and changed. And not just mental, physical, all kinds of different models. So also, it's really difficult, but it's completely essential, in my class at least, to connect observable behavior with properties at the atomic level. So that's sort of my overriding theme in my class. What do we see happening, and why is it happening on the micro level? So I think that in broad terms that can be extended to pretty much any discipline. For me, I take it very literally. What are we literally seeing? What's literally happening on the atomic scale? And that's actually, as I'm sure a lot of you know, really hard for students. It's really hard for adults, but it's really hard for students as well. Furthermore, this atomic level thinking is really necessary for future success in later on in chemistry and later on in the sciences, and really just as sort of abstract critical thinking skills. These are important skills. There's a big push at the AP level to have students think on the atomic scale, because there's a big push at the college level to have students think on the atomic scale, or so I'm told by people that developed the AP exam. And of course, finally, even with the best technology, we can't literally see atoms. So one of the things I really like about simulations is that it sort of drives home that point that the best we can do is sort of model these ideas and try to come up with something that represents these ideas, but also reinforces that these shouldn't be taken literally true, and you'll literally as true. And you'll see when we look at some of the simulations that I use that they're nice because it's very clear they're not literally true, right? They're cartoons, they're animations. So what are some of the things that I do in my class? So I kind of use simulations in three broad ways in my class. The first, which is my favorite, which is what I'm going to demo for you later, is a macro level demonstration coupled with a micro level simulation. So this is the one I've been using for the longest, sort of the approach I've been using for the longest. It's what I find to be the most successful, maybe because I've been using it the longest and I've gotten better at it, I'm not sure, but I find it really useful to sort of show students something that they can all see on the macro level, and then show them what's going on the atomic scale using a simulation, and that's much of what I'm going to show you today. Another thing I like to do is worksheet guided pair work with simulations. So if you're a science teacher, inquiry-based is like the big buzzword, the thing we're all trying to achieve, but I think a lot of us don't really know how to achieve it, or at least I'm not exactly sure. So this is something that I work a lot with, and I think it's really nice for students to really just play with simulations. And in chemistry, where it can be dangerous to say, here's 10 chemicals, play with them, you can't really do that, right? You can do that with a simulation. You can say, here's 5 acids, play around with them, see what they do, right? And obviously the stakes are very low. So if you mix 2 things that will create an explosion, it's not a big deal on a virtual simulation. So I have my students do a lot of that. This is also great when you're not there. So this is what my students are doing today because I'm not there. So I can give this to a sub and give them the computer cart and the handouts, and the students can do what they would have done anyway, even if I was there. And it's really minimal for the sub. You know, I give an answer sheet so that they have an idea of what's going on. Something I have used less, but I'm starting to use a little bit more, are virtual labs. And I want to be clear that I think in no way is this a replacement for the actual lab experience. I don't even think it's a substitute for the lab experience, but it's great for a few reasons. If a kid is out sick for a long time and misses some labs, I just recently had a kid who had a concussion and was out for weeks, and so this was one of the ways that he sort of kept up. He did a few of our acid-base labs virtually, right? So that was really great. It's also nice, again, if you have safety concerns or limited access to certain things. We're fortunate enough to be at a school that's really well stocked in terms of equipment and chemicals, and I can order whatever I need, but when I was in the public school system, it was a little harder to get my hands on everything I wanted, so this was a nice option. But it's not something I'm going to talk too much about because it's not something I use a whole lot. So I'm certainly, not that I'm an expert on any of this, but I'm certainly not an expert on that. So what are the resources we're going to look at? The one I'm going to show you most of all are PhET simulations. I love PhET simulations. So these are from the University of Colorado. So the web address for their general site is phet.colorado.edu. PhET stands for, I did a little research on the history yesterday, Physics Education Technology, because it started as a physics project. It's since expanded. There's now physics, chemistry, math, biology, geology. These are just some of the things that you see as soon as you go to the website. I'm amazed at how often they're adding things. So even as I was developing this activity here, I was going back to their website and there would be new ones all the time. So some are better than others, some are a little less intuitive than others, but they sort of have this constant tweaking process that goes on. They actually, it's research-based how they develop these. They do it in collaboration with students and with teachers. Students work with the simulations. They're all supposed to be very intuitive. You're supposed to be able to sort of manipulate things like you would in the real world. There's dials, there's meters, there's things that you can move a slider on. And they develop all this, it's all based on the Bransford book, How People Learn, if people are familiar with that. I know it's a very popular book these days. They have a newsletter, they have a Twitter feed, they have a Facebook page, so if you're interested in following the PhET process, there's a lot of information about their development that's interesting in its own right. I'm not going to get into that, but I encourage you to check it out. It's really interesting to see. I'm going to show one homemade simulation I made using PowerPoint. I like these because I can show exactly what I want to show, right? I don't have to like rely on someone else to sort of have been in my brain and made exactly what I was shooting for. Also, you get a little bit of like credit with the students. They're kind of impressed when you say, I made this. Even if it's really, really low level, you get some oohs and ahs. It's kind of nice. One that Susan uses all the time, Susan, the one who's not here today because she's ill, is Iowa State Chemistry Department, Tom Greenbow. He's a professor there. He develops all these simulations. She does this great virtual lab with the activity series, so reactivity of metals. That's really, really good. And unfortunately, she's not going to be here to talk about it, but I did want to highlight that as another resource. And all these resources are linked to our NICEACE webpage, the portion of this conference's webpage, including the Greenbow stuff. So I'm not going to talk about that, unfortunately. But again, I encourage you to check that out. And he says on his website that some simulations are meant to be for lecture, so there's like no instructions. The teacher just shows them, and you know, supposedly you understand how it works, obviously, so you don't need the instructions. But then there's also many guided activities for students. So he has sort of two types of simulations. I think Susan mostly uses the guided activities for students. So I encourage you to check that out as well. All right, so I'm going to switch to our website, which is, for some reason, sort of not completely being displayed here, but let's see. Well, you can see most of it, I suppose. I think you'll be able to see everything that's important. So this website is linked to our NICEACE website as well. So under the 10th grade tab, you'll see these are some of the simulations that Susan and I have used repeatedly. So I'm going to start by talking about this mole ratio one. So this is an example of a homemade one. Again, pretty low tech. So one thing that I have learned with using simulations is I want my students to be able to write in words about what they see and what they don't see and how they connect, and I also want them to be able to draw pictures. My students are surprisingly hesitant to just dive right in and start drawing things. I think there's a lot of nervousness, well, what if I get it wrong? And no matter how many times I say I'm not grading this for correctness, I'm grading it for process and things like that, they're still very hesitant to just start drawing something. So I found that it's really crucial to do a lot of scaffolding, show them what I mean by drawing an atomic level diagram, and I realized that I was taking a lot of that for granted in the beginning. I assumed they would know, draw little circles, these are atoms. No, they don't actually, it's not that they don't know it, but they're nervous that they're not going to do it right, or at least this is what I see with my students. So this is something we do sort of early on. We've already drawn with phases of matter, drawn things like solid, liquid, gas, distance between particles changing. So this is an intro to mole ratios that we look at. And what you're going to see in this short video is I'm going to start by doing a macroscopic reaction. So it's the combustion of magnesium, which is, if you've ever done this before, it emits a really, really bright light. You tell the students 10 times not to look directly at the light, and they all do, and then they say they see spots and get a headache, it's a big thing. But it's totally harmless, it's just really, really bright. So it's like if you look at a camera flash, it won't be that bright on the video, obviously, you can look directly at the video. So this is a reaction they've seen before, which I really like to bring those back, and this is the first time we're looking at it on the atomic scale. Apologize for my editing. I'm not an iMovie pro, so it's a little sloppy editing here, but I think you can get everything you need.
So this time I want you to think about not just what you're seeing, but what you're not seeing. So the handout I'm giving you asks you to think about the reaction that we're going to do on two levels. The macroscopic level and the microscopic level. So what's the difference? Macro and micro. Alexander?
Macro
right.
Atmospheric magnesium reaction.
Now that you've seen it on the macro scale, take a few minutes to please fill out the whole front of this sheet. So, describe what you've seen on the macroscopic scale, what you can see, and then at the bottom I want you to think about the part that you can't see. So you can yell it out. How many magnesiums do we have? 6. How many oxygens? 8. 9 I thought I had. 1, 2, 3, 4, 5, 6, 7, 8, 9.
Yep.
Hard to count through sheets, I know. This is before the reaction. Nothing's happened yet. This is before the reaction. How many, those are oxygen molecules, yep. How many magnesium oxides do we have? 0. Right, we haven't made any yet. Okay, you ready to be shocked and amazed? Ready? Yeah. Sorry? So the magnesium is atoms, right? Because they're individual atoms of magnesium. But the oxygen comes in molecule form, right? Okay, here goes. Now the reaction is occurring. Alright. So now take a second and fill out the second row for the after the reaction. So how many magnesium atoms do we have left? 0, right? I know there's some in the compounds, but we're just looking for elemental magnesium. So there's none left. How many oxygen molecules do we have left? 6. 1, 2, 3, 4, 5, 6. And how many magnesium oxides do we have? 6. 1, 2, 3, 4, 5, 6. Okay, now having seen that, I want to know if your ideas of what's happening in this reaction have changed. So please take a few minutes to fill out the rest of this.
So the sheet that I'm referring to throughout this is one of the two sort of models I use. Sometimes I ask them to draw pictures, as I said. Sometimes I ask them to write in words. So here they're being asked to write in words. I ask them macroscopic, what do you see? Microscopic, what's going on? And then I do the demo or the simulation, and then I ask them, now what do you think, right? And then I ask them several follow-up questions. So one of the things that's great about this example here is in the beginning she's talking about gas being released. So she says there's all this gas released. And then later on there's no mention of this gas. Now of course whether that means she's really figured this out remains to be seen, but it was an improvement to my mind in terms of her understanding. And there's also an improvement in the language. She's referring to molecules, she's referring to atoms, where before she wasn't referring to molecules and atoms. So this is, as I said, an entry into this topic. From here, we refer back to this reaction all the time. When we talk about limiting reactants, we talk about the fact, hey, there were some oxygen molecules hanging around, what was going on there, what ran out first, what was limiting. So I keep coming back to this. So that's that one. I feel like I'm running long here, so I'm going to jump back to another example. This is an example where I have students draw what they see. So this is really embarrassing, but even though these videos are taken on completely different days, I'm wearing the same outfit, which I didn't realize till I went to edit them. I'm like, I don't even like that shirt. Why am I wearing both of these? So these were not taken on the same day. These were taken weeks apart. I did do laundry in between. So this is an acid strength activity that we do. So this is actually a follow-up to the demo that I'm going to do for you guys in a minute. So I'm going to ask you to sort of think in reverse here. I'll show this, and then we're actually going to do what was the precursor activity to this. So this is actually an exploration of acid strength. So it's looking at dissociation of molecules, or dissociation of ions, I should say. In the beginning, I used two simulations here. In this part, I'm using the simulation that I'm also going to use with you guys. So I'm going to breeze through that part, and then the second part, I'm using a different simulation. These are both PhET simulations from that PHET website, so as I said, I really like these. So this is sort of the intro to the lesson.
First of all, what will happen if I put NaCl in water and put it up to the light?
Oh, a student is videoing this, by the way.
Natalie. It will light, so let's see. Little NaCl.
On his iPhone.
So what do I need?
Water. Water.
That's the kid that's videoing.
A little bit of water, swirl it up. Ready? That was well timed, Fred. Thank you. Okay, so please take a minute. Think way back to when we did this before and we discussed this. And please fill in that first box on your sheet. So you're being asked to do two things in that box. You're being asked to draw a picture of what you think happens to the NaCl, and then you're also being asked to think about what happens in terms of concentration. So there's a graph on the side. Take a stab at this. If you're not sure what to draw, draw something. You will not be graded for correctness on this activity, so please try to draw something.
Okay, so the purpose of that section of the lesson was to remind them of something they've already seen many times. They've seen the conductivity apparatus, they've seen the salt, they've seen the micro-level version of the salt. I do show it again after this, but I'm going to show it again to you all in a second. Then we move into the new material.
I'm going to start with some HCl. So we're down on the chart now. So there's a chart on your sheet. So the first thing we're going to start with is HCl. And HCl, acid or base?
Acid.
Acid, thank you. Is it a strong acid or a weak acid? Strong, right? So we know this. So you can fill that in on the chart as well. Here goes.
Yay!
Alright, so please write down what you have witnessed. This is acetic acid. So first of all, anybody remember the formula for acetic acid? Lily. CH3COOH. Very good. It's the acetate ion with a hydrogen. So, it's full of acetic acid. So acid or base?
Acid.
Acid. Do we remember if this is strong or weak? Weak. This is a weak acid. You eat this acid. What is this? Do you remember? Vinegar. It's vinegar. Very good. Every sample of water has a few OHs and H3O pluses. So how is it possible that this is still neutral? Think back to what we did the other day. How is this still neutral? Think about the definition for neutrality that we came up with. Alexia. Very good. So notice you've got 2 and 2. These are equal, so it's still neutral. If I put equilibrium concentrations on here, the concentrations are equal. Is everyone? So notice that this strong acid is any generic acid. Remember, A is not any element, right? So HA just means H and the rest of the acid. If it were HCl, A would be the Cl. If it was HNO3, A would be the NO3. Are we okay with that? Yeah. Okay, so please take a second on the next page of your sheet to the best of your ability, sketch something like what you see in the magnifying glass. Let's take a look at the weak acid. So, notice there's some differences here. How is this different? Fred, what's different?
pH is 4.5.
Okay, the pH is different. Very good. What else is different? Anybody ever heard from yet today? Maybe Lily. What else is different?
I think in the other one there weren't any HAs. They were all dissociated.
Ah, very good. So we've got a goodish amount of HAs in here. Please take a second to sketch this one and then also do the bar graph. I'll show you the bar graph in a second. I'll give you some time to sketch it with this one.
So it was one of my more class clownish sort of students videoing that, so I apologize for the quality. So this is the sheet that they're using. We start out here by sketching the thing they already know. This is the NaCl. Then they sketch, Then they sketch the strong acid and the weak acid. Then I ask them to write about what the difference was. So to drive the point home, the thing we're shooting for here is strong acids dissociate completely, weak acids do not dissociate completely. So that's what we're shooting for. And then finally, as an extension, what would a base look like? So I don't show them the base. What would that look like? What would a strong base look like? What would a weak base look like? And then summarize in a few sentences. And I tell them less is more, so I don't push the sentence thing. I try to get them to the point. To talk about what the differences were, how all these things relate. So conductivity, dissociation, and acid strength. How do those 3 concepts that we've been looking at all tie back in together? So this is an example, like I said, of a place where I'd have them draw things and write about things, some of which they've seen before, some of which they haven't. So the last thing I want to do for my section here is actually do one of these demos. So I'm going to use the PhET simulation, and if you are on a laptop, I encourage you to also run this at the same time. So I have not pre-opened it on my laptop, so that you can, so we can all do it together. I don't know why this won't scroll over. So the website.
Arrow keys. Use some arrow keys.
That has to do with your display settings.
Yeah, it's for not set right for this one, I guess. Well, in any case, it's http phetcolorado.edu/en/simulation/ and then it's sugar and salt solutions. I think that last word is solutions. So I'm actually going to go to it, and you'll probably be able to see the whole thing yeah, you can see the whole thing in my. Is that the right one? That's not the right one. Sorry. This is the one I want, salt versus sugar. So now you can see the whole thing in my bar up there. So just a few things to highlight on this website. I won't scroll down yet, so you can all copy that down. When you go to the PhET website, I usually just type in a search term for what I'm looking for. So I'll type in conductivity or salts or something like that. And anything they have related to that pops up. You won't just get simulations. You'll also get a few other things. You get activities that other teachers have designed. And full disclosure, every worksheet I showed you on that website was adapted from another teacher. So I don't take full credit for any of those. And they have been credited on the website, just so that you all know if you're looking for the original source. You can find them. Some I've updated heavily, some I've updated just a teeny bit. Okay, so I'm going to scroll down a little bit. Other things that you should be aware of when you go to an actual simulation. They always give you some learning goals, which are pretty helpful. The teacher's guide is great because it sort of draws your attention to things that you might not have realized about the simulation right off the bat. Once you open the simulation, there's no like directions, right? It's just right. There's nothing. There's no words. You just start clicking and start doing things. So the teacher's guide is helpful, particularly for some of the more advanced ones. So you know what's going on and what they intend, right? Also, some teaching ideas. So under teaching ideas, this is where I get a lot of the worksheets, the lesson plans, things like that, and related simulations. So salt and solubility was the one I opened up before by accident, which was pretty close. So I just run now. You can embed them. I don't download them because my security settings don't allow me to. I imagine I could change that, but I don't. But it works just fine to run it. So I download it to there. You need Java, which I feel like I need to update every time I use this. Java's always telling me there's a new version. Usually you can run it even if you don't update Java. I've never run into a problem by just saying, I'll update later. So, I disabled all these, but. So it should pop up in a second. While I'm waiting for that to pop up, I'm going to bring out some low-tech technology really quickly. So there's our simulation. So this you saw in the video. I love this thing, if you haven't figured that out. I use this all the time with as many applications as I can. And the kids get really excited about it. It's a light bulb, but they really get excited about it. And it brings up a lot of really good questions. So if you're a science teacher, you probably know exactly what this is. But if you're not, it's just a light bulb with two leads. I'm not going to touch them because if I do, the current would go through me, and that would be bad. But it's not lit right now. It's plugged in, but it's not lit because it's not a closed circuit. So what this allows you to do is experiment with different things that can close the circuit, right? So obviously air does not close the circuit because otherwise it would be lit. The electricity can't flow from one side to the other. So what I usually start with my students when I do something like this is I start by asking them, let me go back to our website, start by asking them to draw a chart like this. So a lot of what I do with these simulations with the micro and the macro is let's make a chart and come up with patterns. So this would be sort of an intro to this sort of thing. So I ask them to make a chart, they fill in the substance as it goes, whether or not it lights, whether or not it dissolves, and how bright the bulb is. I do this with a bunch of substances. I'm going to do it with 3 today because you'll all get the picture really quickly. But with the kids, I do it with a bunch of stuff. So I'm going to start with just water. So in the classroom, I used deionized water so I can get the point across that there's no ions. It's been deionized. But, ooh, this should not light. Oh. All right, Evian, what's in your water?
There's a lot.
Yeah, that's interesting. Okay, so let's all pretend that didn't light. I wonder what is in their water. All right, I was worried I wasn't going to be able to get tap water here, so I bought this. Well, that's going to kind of destroy my plan here. So then I would put some salt. I would obviously use proper safety procedures and equipment and wear gloves and things like that, but I'm not going to here. So NaCl in water, I asked them first, does it dissolve? So I would start up, I'd walk around, ask some kids to talk about it. I purposely don't let all of it dissolve because I like them to realize that some will dissolve and some won't because there's saturation, there's only so much the water can hold. and then I light the light bulb. And I have them record that.
Seems distinctly brighter though.
Exactly. Nice. That's exactly what I'm shooting for. So it should. So then in the brightness column, they would fill in that that is a bright light. I usually wash it off in between. So yeah, for comparison's sake, salt, plain water, which shouldn't actually light, but apparently there's more electrolytes in Evian than I had realized. And then I do sugar. So I usually do this with several sugars and several salts, and I also do it with things that don't dissolve at all, like sand and things like that. The sugar should, again, not light at all. You're seeing the water, which is causing it to light a little bit. So I do that, and then from there, I show them the same thing on here. So you can actually do the macro part, the part that I just did with this, on here. I don't like to do that because I like the real thing. On the smart board, you can actually shake it. The salt comes out. That's kind of fun. You can't see it on here because this is the macro version. This is the macro version on the computer of what I just did. You can see the brightness will increase as I add more and more salt. Right? So this is the simulated version of what I just did. I don't particularly use this, as I said, because I don't see the use in redoing the macro, but it is there. What I do use is the micro. So I start with the salt because that's what I started with here. You shake the shaker. Come on, shaker. You get some salt. Some cool things you can do. You can pause it as it hits the water so you can actually see. So what they're supposed to take home here is that salt dissociates and sugar does not. So you can actually see the dissociation happening. You can run it forward very slowly.
Is there anything like this that works on the iPad?
So
I feel like a lot of these stuff are
from?
done. Yeah, sorry.
No, I was like, someone's talking. I couldn't figure out who. I have not found anything I like as much on the iPad. So there are, first of all, our students don't all have iPads, so I don't explore it as much as maybe schools where everyone has an iPad would. So I don't know that I can give you a good answer, but what I found in my experience is I don't see anything that I like this much. So, but I'm sure there's something. There's got to be, right? You would think. So you play it, they run around. You can see the concentration here, which I love. This actually you saw in the acid strength one where they had to do a bar graph of the concentration. This is my favorite part because we do a lab on separation of mixtures where they have to dissolve salt and then get it back. So you can, come on, all right, I'm going to move full school way. You can evaporate the water and you'll see that the ions reassociate, which I think is awesome because they do that, and so this also drives home the physical versus chemical change point, which is the point is there's so much that you can get out of this. So then I reset it, switch to sugar, which I love. It turns into a sugar shaker instead of a salt shaker. They think of everything. So you'll notice with the sugar, they do not dissociate. The molecules stay together, which is the whole point of this entire lesson. Obviously, I don't say that to the students. It's for them to figure out. But from here, we would talk about patterns we saw on the macro scale, how those relate to patterns we saw on the micro scale. And I usually end with write a sentence that summarizes how dissociation connects to conductivity, connects to different types of substances, bonding, things like that. So I am running over my half of time here, so if no one minds, I'm just going to breeze through. There's not much that I wanted to say about AP aside from the fact that I really like it in AP because at my school, at least, it's a second-year chemistry course, but many students haven't had chemistry for 2 to 3 years, depending on when they took it the first time around. So it's great as a refresher. I can say, go home and play with this, and as seniors, they're all more than capable of figuring out how to use the FETs and solve troubleshooting any computer issues they run into. They play with them in class a lot. As sort of a what do you remember from this? So this last week they were doing what do you remember about equilibrium, right? And playing with the FET simulation to sort of refresh their memories. Likewise, some of these are really advanced. So this discharge lamp one is actually an activity that's used at Ohio State University in their general chemistry course. So some of them are college level. So I use that activity, I really like it. It's like neon lights kind of thing, it's really neat. So I'm gonna stop there so I'm not cutting into your time. Does anybody have any questions about the science side of this or anything I talked about? Yeah.
Just a quick question. Do you find that it's really enhanced your practice and helped your students really understand?
I do.
the information?
I think, so I ask my students all the time what they think, and I think there's some students that are like, oh, it's neat, it doesn't change much for me. But some students are like, yeah, I really get it. And it never detracts, right? So I think for the students that it really helps, it's worth it. For the other kids that see no
Sure,
change.
absolutely.
And I think it's really helped me too, sort of, because I want that micro-macro connection to be such a driving force in my class. This is a very easy way for me to really do that. You know, I'm often skeptical, like, am I using technology for the sake of it? But I really do think that this is worth it to me.